Okay, good morning, everyone. I welcome you to the third webinar of Simulations with DesignBuilder webinar series. I am Amanda, and I will be moderating today's session. In this webinar, we will discuss how simulations can be used to analyze passive techniques to reduce the cooling load. We will also learn how to model HVAC systems incorporated with natural ventilation for mixed mode operation. Before we begin, I would like to thank our program supporters and affiliates for this year. These organizations have provided immense support to Solar Decathlon India and catalyzed our transition to a net zero future. Today, we have with us PC Thomas. PC Thomas is the founding director of Team Catalyst and also adjunct associate professor at University of Sydney. He specializes in integrated building design using simulation tools to assess and design and delivery of sustainable buildings, in particular in predicting the performance of mechanical services. He has master's degree in mechanical engineering, 30 years of consulting, research, and teaching experience in sustainable buildings, building energy simulation, energy auditing, energy efficiency in buildings, and solar energy. Hello, PC.
Hi, Amanda. Hi, everyone.
Yeah. Now, we will also have presentation from Mansi Parikh. Mansi Parikh is a senior sustainability consultant working in the field of sustainable design. She has key qualifications in the field of passive designing, low energy cooling and HVAC systems, lighting and daylighting design. She has worked on various projects with goals leading to net zero energy, water and waste. Due to some unexpected circumstances, we will be playing the pre-recorded video of Mansi's presentation. If you have any questions for Mansi, please feel free to ask PC Thomas here and I will try to our best to answer them. So now we will start with Mansi's presentation first, and then we will have PC Thomas take over.
So in this presentation, we will be discussing design for natural ventilation at master planning level, passive design studies using shoebox model for various orientations, window to wall area ratios and shading depths, design for natural. So as you know, wind speed and direction plays a major role when we design for natural ventilation in any space. This chart here shows wind direction and wind speed for 3 seasons, summer, monsoon and winter period. As per climate analysis done and discussed during session 1 in Delhi, the occupants would feel more comfortable with elevated wind speed during high humidity conditions like summer and monsoon. So in order to do this, buildings should be oriented to catch monsoon and summer winds, which are specifically from west direction. So after studying which is the major wind direction, we do simulation studies at master planning level to understand the wind flow and pattern in a particular space and to provide recommendations if required. So these are the master planning studies. So these are the wind master planning studies which were done. So as you can see here, at master planning level, this was conducted in Butterfly, which is plugged into Rhino, which is based on simulation software called OpenFOAM. The wind direction considered for this study was again west. The legend shows wind speed from 0 to 0.5 meter, 0 to 3 meter per second, where the darkest blue color that shows almost 0 to 0.1 meter per second of wind speed, and the maximum 3 meter per second is depicted by red color. For wind-driven ventilation to work, negative wind pressure should be formed on the wind direction, and positive pressure should be created on the other side. Wind pressure is directly proportionate in cases with wind speed. This section was cut at 1.8 meter from ground to study pedestrian comfort and provide recommendations. For few spaces, there are low pressure zones which are formed on both sides of the buildings like these. So to improve the natural ventilation, it is proposed to provide passageways. So it was proposed to provide passageways to improve the natural ventilation. Openings are suggested at 1.8 meter to improve pedestrian comfort in these kind of courtyards. For the same plan, this section was cut at 5 meter level above the ground level. This was this was a proposed utility block area. So this would house organic waste composter bins, diesel generators, etc. So since it is in the windward direction, it was recommended to relocate it into a different position in the campus. Now again in these two blocks, these are the dining and the gym area. Both of them are going to be naturally ventilated spaces. So it was recommended to provide breezeways to improve natural ventilation in both of these spaces. Once the passive design strategies were selected, post climate data analysis, which we discussed in session 1, these studies for orientation, shading, WWR were conducted to understand the impact of these principles that also aided to help client and architects to show the impacts of these in the design process. This chart shows cooling loads on y-axis or for various orientation, that is northeast and southwest, northwest and southeast, north-south and east-west. Longer axis. Client to orient maximum amount of buildings with east-west longer axis to reduce energy consumption, as it is the simplest way to reduce energy consumption if possible. Now again, the studies were done for the same model with east-west longer axis, for the same model with east-west longer axis, window to wall area studies were conducted to derive optimum window to wall area ratio to reduce energy consumption in air conditioned spaces. Windows to wall area ratio for a facade can be calculated by dividing total window area with total wall area. 4 cases were studied with WWR of 60%, 50%, 40%, and 30%. The y-axis here shows annual cooling consumption in kWh. By providing window to wall area ratio of 30%, we can almost reduce energy consumption by 14%. Also, this combination would improve daylight in a particular space. Hence, WWR of 30% was proposed to client specifically for air-conditioned academic block. After WWR studies were conducted, optimization for shading device was done. This study assisted in showing climate and this studies assisted in showing the client and architects importance of shading device in reducing energy consumption. 4 cases were studied for east-west longer axis with 30% WWR, like no shading, the case with no shading, horizontal 1 feet shading, 2 feet shading, and 3 feet shading. It was found that case 3 with 3 feet shading depth was optimum for WWR and this particular WWR and orientation. However, the difference in energy consumption between both of the cases was very low. Case 2 specifically with the 2 feet and 3 feet shading device. So 2 feet of shading was very low. However, providing 3 feet of shading device is difficult in terms of architectural design. So, and would also come at an added cost. So 2 feet of shading device depth was suggested at this particular, for this particular orientation. Facade. So for facade, after wind studies at building level, these studies are done at the facade level to understand the wind movement in a particular space. So this design is for an academic block where the courtyards are conditioned, where courtyards are unconditioned across the year and naturally ventilated. So CFD studies for internal spaces were done to understand wind flow in these spaces. The studies were conducted with wind speed of 3 meters per second and west as a wind direction. This was decided based on the climate studies. These were the balcony spaces with 80% openings, and corridors were opened on the both sides. The legend here shows wind speed from 0 to 3 meters per second, with red at maximum wind speed of 3 meters per second and 0 at the least, or 0 to 0.1 meter per second, which is not felt by the human body. So as you can see, there are dark blue patches which can be seen in the balcony areas, which shows 0 to almost very little air movement in the space. So to improve the natural ventilation in the corridors, these are the recommendations which were provided. So like filleting the edge to improve the ventilation in the corridor, splaying the corners to create the wind tunnel effect, increasing the depth of the opening, smoothing of all the niches and continuous wall surfaces, directional curves to direct the wind flow. These are the results of the facade alterations. As you can see, this is the base case and this is the recommended case. The image, the dark blue area on both the balconies has changed. Here, these are the, for the recommended case, the light blue area has been increased in both the balconies, which shows elevated wind speed in both of these areas. Also, there has been an improved wind movement in these corridors as well by providing these recommendations. So hence this case was taken up by the client. Now the studies were done after this. Studies were done for after designing for window sizing. Studies were done for dining area to optimize window opening area. The dining, so these are the dining area. This is going to be a naturally ventilated space across the year. In case 1, windows are open 100% of the time. Say these are side hand windows. Whereas in case 2, windows are open for almost 50%. Say these are the sliding windows. And annual hours where ambient temperature was going above 33 was calculated. So these are the results from these studies. These temperatures are more than these 10% is, say 10% is more than where the ambient temperature is reaching more than 33 degrees Celsius. And again, this 33 degrees Celsius is taken from, this is the upper limit for India model for thermal comfort, specifically for Delhi. To understand more about this model, you could visit self-learning modules. So as you can see, where case 2, as you can see that 15 to 20% increase in discomfort hours were observed for windows with 50% clear apertures, say for a sliding window case. So openable clear windows were recommended to the client.
Okay, so that was the presentation from Mansi. We will now have PC Thomas present, and then let's learn how to design HVAC systems.
Hi, Amanda, and everyone else. Now, there were 2 small sessions that are on for today. So I'm just going to switch microphones. Hold on a minute.
Yeah.
There we go. So what we're going to do is look at first an ideal air conditioning system. And then secondly, we're going to look at natural ventilation. So that's probably the easiest way. Let me just open this model and share my screen. So here is my screen. And let me open. I've got two different models set up. And we'll work through them. The first one, I've set up a small commercial building, and that we'll use to look at an ideal air conditioning system that you can do in DesignBuilder. You can do detailed as well. We'll do that in the next webinar, but we'll do the ideal one. And we'll try to address some of the things that Mansi was showing us in her presentation. Okay. So here is my model, and I've kept it at a single floor. We'll put a couple more floors on it. But if I make all the adjustments in the simpler model, then as I clone the different floors, then it will carry all these things along with it. So if you guys remember an early part of what I showed you in the first lecture, and I showed you that you can go and see the videos for that lecture online. When you do air conditioning, you have to think about what are the reasons why you need air conditioning. Why does a building or a space become uncomfortable? And for that, I remember showing you this picture, which I'll just put at full screen now. And in this, you can see that there are 4, we call them loads, cooling loads or heating loads. And typically one is about how much sunshine comes into the building. The second is about what are the things that are generating heat inside the spaces. And so that can be people and equipment and lighting. These are very typical loads. Then there is a heat flow because the temperatures are different between the inside and the outside. And so if it's hotter outside and you want to keep the room cooler, then the heat is trying to get in and you're trying to keep it out. And that's when the building fabric U value or R value becomes important. And then finally, you need air. So if you're in a building, you need to have ventilation so that pollutants are taken away and oxygen is replenished. But you also have uncontrolled ventilation. We spoke about infiltration that cracks around the windows and underneath the door, poor quality construction. So we need to define these things, and then you can calculate what is the amount of energy that's required to keep a space within a particular range of temperatures. And sometimes if you're in a humid location, then the energy needed to keep the humidity within a certain range as well. So let's look at what we want to do in DesignBuilder for that. So here's my model. And it has, at this point, only one big open plan in the floor, right? I'm going to keep it really simple for today. But what I'll do is first we'll define some of the things we talked about. So if you make all your changes at this building, then it will apply all the way across. Okay. So on the activity tab, we have to define these internal loads that I was showing you. So first you need to say how many people are occupying it. We spoke about that last time. What's the schedule for these people to occupy it? But more importantly, we need to say something about what is a thermal comfort range that you are willing to accept. Okay. So in this case, I'm aiming for somewhere between 21 and 24. And what I've done is I've just increased 21 to 21.1, and I've decreased 24 to 23.9. And the reason I've done that is when I'm adding up hours, sometimes you get a number like 21.003, and it'll count it in the higher order. Okay, of course, you can change that, and you need to set that to what is useful and applicable for your design. You might want to say, well, between 18 degrees and 26 degrees is comfortable. That's fine, as long as you do that. Now, don't worry too much about these setback temperatures. We generally, in Australia, we don't use them. But if you do put some numbers in there, just make sure they're a few degrees lower for heating and a few degrees higher for cooling. We'll speak about it later. Typically, in air conditioning systems, we don't control the humidity explicitly. Again, as I said, unless you're in a place like Chennai or Bombay, something like that. So what I'll do is I'll just keep that as somewhere between 10 and 90%. You want to make sure that both these are switched off. We're not going to use any natural ventilation at this point. And this is where the internal loads start to come in. So for people, we've said, what should be the fresh air per person? Again, I discussed that a couple of webinars before, and I've also put some equipment in here. Okay. So I won't deal with construction. We've already done that. I won't deal with windows. We've sort of done that. But what we need to do now is to look at air conditioning. Okay. So at this point, underneath the air conditioning tab, we're going to only be using what we call ideal systems. So we're really not simulating a pump or a compressor or a fan. We're just working out the amount of energy that's required to heat or cool a space for a particular range of conditions. If you saw Mansi's presentation just now, she did 4 orientations, and then they did different window to wall ratios to kind of try and find out which was a better building fabric, which building presented a smaller air conditioning load to be taken care of. Now, what I've done is I've actually put here a template, and this template here is for what we call PTHP, a packaged terminal heat pump. So this system can provide heating or cooling, but it uses electricity for both. Okay. Now, when you switch it on, typically what you'll find is that it removes mechanical ventilation, but we need it. So before you make a run, when you are defining PTHP, please do ensure that you've got mechanical ventilation switched on, okay? And when you switch on mechanical ventilation, it wants to know how are you specifying the minimum fresh air into these spaces. Okay, and there's a number of options here. You can leave it at number 4, minimum fresh air, some per person plus per area. And what it does is that it goes to the activity tab, and then it looks at each zone and says, okay, this is the minimum fresh air that has been stipulated. So in this case, I've only got 10 liters per second per person for fresh air for the per person requirement. And I've put 0 for a liters per second per meter square. So I'm not adding any fresh air based on the floor area. I'm only adding fresh air or outside air. In many cities, it's not fresh. I'm only adding that outside air based on the number of people who are going to be occupying the zone. Now, in order to calculate the energy for heating and cooling, it also needs to know these office equipment, number of people, and lighting energies. Okay, so I've got some very efficient lighting, 4.5 watts per meter squared. I've got reasonable amount of equipment, and again, this could change if your people are not using laptops, if they're using some other kind of more power hungry computers or fax machines or printers, or if they're doing some cooking in the space or something else, you may have to find some other value. And your NBC, National Building Code, should give you some of these values. If not, ISHRI in India will give you these values, typical values for India. Okay. Now, so I've got the HVAC set up, and here what I'm doing is, if I want heating and cooling, you can tick both of these. If you're in a climate where you don't have any heating needs, or you don't want to work out what the heating needs are, you can just switch off the heating, and then it doesn't calculate anything for heating. Now, there are some other things to be input. The defaults are pretty okay. You don't need to change anything for heating. For cooling, you may want to make some slight changes. And what I suggest is that the supply air temperature, the minimum supply air temperature, can be kept at 12 degrees. That's fairly common. The minimum supply humidity ratio is probably a little too low for tropical countries like India. So you may want to put that as 0.010, which is actually 10 grams of moisture per kilogram of dry air. Okay, so if there are mechanical engineers amongst you and you understand what a psychometric chart does, in a psychometric chart you get properties of moist air. So 10 grams and 12 degrees centigrade is a good supply air condition to design for. Okay, so I'm going to put that in. Now, the other thing to be aware of is that you want to, this schedule isn't actually telling the simulation what temperature to control to. Okay, it's called an availability schedule, and all it's doing is it's telling the program when air conditioning is available. Okay, so if we look at this schedule here, what you see is that I've got, okay, I've said that all the way from January 1st till December 31st, for 3 special dates, weekdays, a summer design day, and the winter design day, I'm allowing air conditioning to be available between 7 a.m. and 6 p.m. So before 7 a.m., so until 7 o'clock, it is 0. Between 7 a.m. and 6 p.m., which is 18 hours, it's 1. 1 means it's on, 0 means it's off. And after 6 o'clock, after 6 p.m., it's off. Okay. And then I've kept it off for weekends and all other days. So that's my HVAC availability schedule. You must develop one and you must put it for all 3, the mechanical ventilation, the heating, and the cooling. Okay, so the same availability schedule for air conditioning for these 3. Okay. Now, when you build schedules, you must be very careful about the type of the schedule that you're using. Okay, and I recommend to you that for this one, the availability schedule, you use the fraction schedule. You have temperature, fraction, any number. There are some different types of schedules. You can read about it if you go to the help file on F1 on the right-hand side. But I recommend you use fraction. Okay, and fraction means you can only put values between 0 and 1. That's what we're doing. You can put 0.5, 0.6, etc. But for availability, we only say either 0 off or 1 when it's on. Okay. So what we can do is just to check that everything is working correctly without making any zones, etc. You can do a quick run here. Okay. So I'm going to do a simulation run, and I should say these things, couple of things here. I've got this thing to be set up in Bangalore. Okay, so if I look at the location tab, you'll find that I've selected Bangalore, and it's using an ISRI file to do the energy simulation, and it uses a design day, which I'll cover in the next webinar we have. I'll cover that in more detail for sizing system and so on. In this case, we're not interested in sizing. We're really looking at energy consumption. So back to the building level. And when I go back to building level, I get many more tabs. When I'm on the top level, you might have seen that there were only 3 tabs there. Now, the Mansi had said that they had tried different orientations and different window to wall ratios. So this one, if I go to the openings tab, I've used a 40% vertical glazing that ASHRAE has in Appendix G. If you look at it, it says window to wall ratio 40%, window height 1.5%, window spacing 2.5 meters, sill height 0.8, no reveal depth. And if you do that, then it will try and fit the window to wall ratio within that building. So it's very good for your early massing studies, etc., just like Mansi was showing us. I'd suggest you remove any frame and dividers. I'll show you why in a second. And right now, we're not using any shading devices. Okay. Now, the type of window that I'm going to use, and you can certainly use any type that you want to. And what you can do is, if you put this window definition using the simple window definition, so it's quick. And for most things, that's sufficient. You can then just give these 3 key values, and that's enough for the model. Even though it says the definition is simple, it's not a really simple model. It's quite complex under the hood. Energy Plus has got a really complicated model where it looks every hour at the technology that fits within these 3 design parameters, and it works out an incident angle modifier curve. Okay, so what I'll do is, for the first run, we'll make it a little inefficient. So I'll actually make a copy of this and rename it. So there we go. I'll just call it an SDI window. And instead of U of 3, I will give it about 5, because that's a single glass window. And I won't have a very good solar heat gain coefficient, so I might say somewhere around 0.6 or 0.7. And then I'll make those changes here. 0.7. Now, light transmission, I don't know, but I'm going to put it close to the solar heat gain coefficient. And if you get hold of some performance data, you'll be able to get these values. The only thing to remember is, I'll double check that it's actually got it there. The only thing to remember is that there is a difference between just the glass data and the glass plus frame data, right? And when you put the numbers in here and you remove the frame and dividers, then we're really talking about the whole Windows performance. See, I've removed the frame and divider value here. Okay, so I think we're good for now. That's 40% window to wall ratio. The only thing we might want to look at is some orientation. Okay, so this one is, north is over there, south is over here. And in India, south is where the sun comes from. And I've got a drawing here of where I might put a neighboring building. So what I'll do is put it on the south. So I'll flip this orientation around so that the adjacent building will be on the south side. If I put a building, then it will cast a shadow, and that might change the energy use. So let's do that. So I'm going to go to the site level or the location level. And in the site details, I'm going to change this 0 to 180. Okay. And if I do that and come back to the building level, you will see that my orientation has changed. And one of the ways to kind of possibly check it is if you go to this rendered view, visualize, and you turn on the sun, then you can see where the shadows are and where the sun is. Okay, so you can see here, the sun is high in the sky in summer, and it's lower in the sky in winter. But being Bangalore, you're closer to the equator, right? And you can see where it is. So if I say looked at summer, June, and looked for the 21st day equinox, then you can see how this is working. Okay. But if you went down to December, you can see the sun is now on this side. So it's a good way to check whether you've applied the right orientation, etc. Okay, let's go back. And for this run, I'll just do the simple one zone model and run an energy simulation.
PC, maybe before you run, you might want to take this question up.
Sorry, I've been
Yeah.
looking at the questions.
Yeah,
Actually,
so
let it run.
Should we take them up later?
No, let's take it. But what I'll do is I'll just get the simulation to start running, and then while it's running, we can take the questions. So, okay. Now let me just look at this question. Aha, okay, that's a good question. There's a couple of questions here. One is, while designing the shading for an opening, how do we decide the critical day for it, for which it has to be designed? Now that's a very good question. It's there is actually no critical day, because as the sun moves in the sky, it has a different impact on the amount of cooling that's required. So you do want to look at sort of the annual outcome. The only time when the shading device becomes critical is when you're trying to size an air conditioning system. So if your shading device actually provides the most amount of shading at a time when the combination of the solar load and the air temperature provides the highest cooling load, or the cooling demand, I should say, on the building, then that becomes a little bit critical. Okay, and between this session and the next session, we'll explore that. I'll actually put a shading device and we can see how the energy use changes. Now, if you saw Mansi's presentation, you can see that the annual energy use for cooling didn't change a lot, changed about 2 or 3%, okay, because of orientation, because of shading, and so on. So that really, hang on, here we go. That really has to do with the location, the building envelope, the internal loads, all of those sorts of things. Once you've got that basic model, then you need to work really hard to reduce the energy use significantly across the year. Okay, so you can see here I've got some outcomes, right? And if I went to a zone, I can see some comfort outcomes. And I'm looking at the hourly outputs, right? So, and if you want to see them somewhat carefully, clearly, you can reduce the number of hours. And you can see, you'll get it on a slider with 7 days, and you can push it through to any place you like. Okay. Now, January is so-called winter in Bangalore, and the dark blue line is the ambient or outside temperature, and then these 3 lines are the average zone conditions. We've only got one big zone. It really doesn't represent it very well. You should break it up into zones, but as a quick exercise, this is good. So where you see this flat line is where the air conditioner is holding the temperature at your design point. Okay, so it's telling me that even in December in Bangalore, this building requires some cooling. Okay, and that's because of a combination of equipment loads and uninsulated windows, right? Because you can see that the air temperature actually drops quite low. At night, it's dropping to 15 degrees centigrade. But that's not being reflected in the zone. Okay, we're in the zone, we're assuming all the windows are closed, all those equipment loads are on, and therefore you can see the temperature doesn't drop a huge amount. But as soon as you switch off the air conditioner in the evening, you can see that the temperature rises a bit. Okay, that's the blue line. The red line is what the people sitting inside feel. That's your radiant temperature. So while the air temperature is around 24 degrees centigrade, what people feel might be much higher. In this case, 28 degrees or so. So that's not very, it's not a good fabric. But, you know, we've got some fairly poor quality windows. I don't know what the constructions are, I haven't checked. This is Saturday and Sunday, and Saturday and Sunday I've scheduled the air conditioner to be off, and you can see that it's traveling much higher than the air temperature. Okay, now once you've done this run, there's a few things you can do. Okay, just give me 1 second. I just need to do, I'll be back in just a sec.
So, yeah, okay.
Sorry. Okay, so now the first time we did this, we looked at how to look at results. If you remember the first webinar we did, we looked at how to look at results. And what I said to you is that if you went to the file and folders and the Energy Plus folder, you'll get some outputs that Energy Plus would have created. And the one I'm going to look at right now is this E plus TBL. That's just an Energy Plus table.html. Okay. So if I open that file, that is actually the standard output that Energy Plus has just created. Okay. It's a searchable file, right? And depending on what you turn on, it will report a number of things. Okay. So if you want to see what's the energy use, if you click on the first one, it'll give you energy use. Okay. And what it will do is that you'll find the energy use for lighting and equipment under electricity, but you won't find any heating and cooling numbers here. Okay. And the reason is we're using a simple or ideal air conditioning system. And what you'll see is you'll see some numbers under district cooling and district heating. And of course, it's telling me that it doesn't require any heating for this office in Bangalore. And you've got to think about that. The office is used only in the daytime. So there's, you know, fairly, there's some equipment generating heat inside the building. Windows are not particularly efficient. So whenever the sun comes in winter at a low angle, it's actually heating up the space. So you need cooling. Yes, it gets cold in Bangalore at night, but then nobody's in the building at night. We're not using the air conditioner at night. Okay. So that's something to think about. If you're in Delhi, it might be that you might need some heating in January at night in the office. Okay, so the one thing that I did want to tell you is that this number that you see, this is not electricity. It's the actual thermal energy that you need to cool the space. Now, if you remember, and even on the DesignBuilder, in the DesignBuilder file, under the HVAC tab, you will see that there is a number here called the COP, the coefficient of performance, okay? And that's a very crude number, which tells you that, because we're not simulating the real compressor, the fan, all that stuff, it just tells you that if you put in 1 unit, 1 kilowatt hour of electricity, then this system will give you 2.5 kilowatt hours of cooling, okay? So it's like an efficiency, but it's not exactly, because efficiency here is the COP is more than 1. And the reason it's more than 1 is because you're not comparing apples with apples, okay? Or you're not comparing the same two things. You're comparing how much cooling energy can be delivered by supplying 1 unit of electricity. So they are both are energy, but they are two different kinds of energy. So in the DesignBuilder interface, if you actually go and look at the numbers, you will see it does provide you numbers. So if I go to the, okay, let's take the run period. So for the run period, it gives me a cooling number, okay, and it tells me there's a cooling number of 45,036, say 45036. I won't worry about 0.8, but that number seems to be very different from what you're getting here. Okay, and the reason is, if you divide this number by 2.5, which is the COP, then DesignBuilder does that calculation for you and gives you that number. So when you're doing your analysis, don't be confused, okay? What Energy Plus is doing when you use a simple air conditioning system, or an ideal air conditioning system as we call it, it works out the thermal energy required for heating and cooling. And because we've given it a COP, because we've said it's a heat pump and it's using electricity for both cooling and heating, then it uses the COP number that we gave it, and it works out this number for you, okay? So easy enough once you know what you're looking at. Now, if I go back to that HTML file, you can see there are a number of other reports, okay? And you can look at, many of these reports if you need them. I would, okay, at this point I haven't turned on any of the monthly energy reports. We'll do that in just a second, okay? And I haven't turned on any temperature reports, and we can do that as well in a second. But back to where we were. The other thing that you can do is go back to the folders, the Energy Plus folder. And if you've installed your results view file, you can open up this ESO file. I think I showed you that in the first run that we did, okay? So that will then list all the variables that Energy Plus simulates, right? And and some of them are quite useful. So when you're doing diagnostics, you can have a look at what's going on. So it opens the HTML file that you saw before, but we are now interested in the hourly results. And I'm going to plot this district cooling function. And you can see that's the kind of cooling it requires. Okay, so in the summer, and it's a little bit earlier in summer than middle of summer, you can see that it requires around 65 kilowatts or 65,000 watts, if you wish. If you look at a particular day, you can then see how the system is trying to cope with the requirement. Okay. Now there's no heating. So if I try to plot heating, I'll get a zero line. Not very useful. If I plot the air temperature from for Bangalore, you can see this is what the outside temperature is. Okay. Now, it's a single zone. So what we can do is we can just very quickly plot the air temperature. So I'll plot it in there. Okay, I don't want the yellow, so I'm going to put the yellow somewhere else where I know what I'll do. I'll make the dew point temperature, which I'm not that interested in. I'll put that in yellow. Then I'll go back and just plot those two. So air temperature and radiant temperature. Okay. And if I look at some summer times, okay, that's probably as good as any. Okay. So if I just remove the yellow so you guys don't get confused, here we are. Okay. We are looking at, what is this? Sorry. I don't need that. Oh, I see. I didn't plot the radiant temperature. I plotted something else. Here we go. That's better. Mean radiant temperature for the zone, and I want the mean air temperature for the zone. Perfect. That's good. So if I look at a day, one day, and take, you can see what's happening here. The air conditioner comes on, and then by 9 o'clock, it's got the air temperature down in control, 23.9 degrees. And then it keeps it in control till 6 p.m. when we switch off the air conditioner, and then the temperature rises again. Okay, you can see that. But two things you can see. The radiant temperature in the zone is much higher than this air temperature. Okay? And you need to improve the building facade. You need to put insulation on the roof, the walls, you need to put a better window, etc. And the outside temperature peaks around this 3 p.m. But the inside temperature might peak just a little bit later, about an hour later. And that's the mass storage of heat, etc. This is good for your diagnostics. Okay, you don't necessarily have to look at it all the time, every time, but it simply gives you a very good idea of what's going on within the space. Now, to do what Mansi did, you don't need to look at this, these hourly numbers unless you want to. What you can do is very quickly, you can change things on the building and do some runs. Okay, so if you looked at this building, you can then either put some shading devices on, or you can put some insulation somewhere, or you can improve the windows, you can change the orientation, and you can get the energy use numbers. You don't need to play around with the air conditioning system. It's a very simple system. You've put it there, it's doing its job. Okay, so maybe I'll do one run, and then we can just see what the impact of that is. When you're doing a real design, you should zone the air conditioner. So you have different zones, and then it'll work out the total for the building. And use some virtual partitions if it's an open plan office. talk to an air conditioning engineer. Usually they like about 4 meters to be a perimeter zone. And then you can work out the numbers as is. Okay. So let me do that second run, and then we'll answer a couple more questions. So what I'll do, the easiest thing for me to check is to improve the window performance. And in this case, because cooling, I need less cooling energy. That means the inside is getting too hot. Okay. What I'm going to do is I'm going to improve the performance of the window. And the way I'm going to improve the performance of the window, I'm not actually going to change the U value. That is, I'm not going to change the characteristic of the window to reduce heat transfer because of temperature difference between inside and outside. Instead, I'm going to change the way that it lets solar radiation come in. Okay. So I'm going to change the solar heat gain coefficient, and I'm going to lower that so less of the solar radiation comes in. And what we'll do is we'll just keep in mind what is this number. So I'm going to write that down. You guys might want to as well. So it's 112,590 kilowatt hours. And as I said, this is thermal energy, not electrical. If you divide by 2.5, the COP, then that's a rough indication of what the electricity usage would be. So let's go into the openings tab. We have only one zone. If you make a change at the building level, it will change at the zone level. So what I'll do is I'll make a copy of this window, and so that I've got the earlier one and this one, and I will change, I'll halve the solar heat gain coefficient. So from 0.7, I've made it 0.35. So I'll do that. Now, I don't need to change the light transmission unless I was really going to do some daylighting studies. But since I don't know, I'm going to say that the light transmission is similar to the solar heat gain coefficient. Okay, once I click that and that, it should apply it. I can rerun this simulation. I'll let it do that. And then while it's doing that, we'll pick up some more questions. Okay. So Priyanka has asked, how should we calculate the electrical load for an air conditioning system? As the system can be automatically on or off with the help of a thermostat based on the internal loads, yes, required. Temperature and spaces can be ventilated with the help of natural ventilation as and when required based on external conditions too. Okay. So Priyanka, there's a couple of things to remember here. When you do air conditioning, it assumes the building is air conditioned. When you do natural ventilation and you switch off air conditioning, then you're doing only natural ventilation. You need to turn both on, and to do that, you need to use what's called the mixed mode operation of the building. Okay, so you need to set your control strategy very carefully. And then you can say that if the temperature within the zone gets to a certain point, then it will close the building and it will air condition it. Okay, or you might say that when the temperature falls below a certain point, again, it will close up the building and it will heat it up. Okay, and that during the time when the conditions outside are within certain certain conditions, then you can switch off the air conditioning and allow windows to open and close as required, or using some explicit control strategy. So most of the analysis we do is not really very helpful unless you do that control strategy to switch between an air-conditioned mode and a naturally ventilated mode, what we call the mixed mode kind of building, and put an explicit control strategy to say when that should happen, and when it's in natural ventilation mode, what should it be doing, okay? So the next, just now what we'll do next is we'll look at natural ventilation, and then we'll try to look a little bit into mixed mode. You can explore it after that. So let me finish this off. Then we'll have some more Q&A, take 2 minutes break, and we'll do the natural ventilation part. So right now, we're looking only at air-conditioned buildings, right? So if I open that HTML file again, then it will give me what was the difference between the previous one and this time. Okay, so annual performance, and see, from 112,000, it has dropped to 92,951. Okay, so that's about, what is that? About 25% odd, 20-25% reduction. And obviously, if you divide this by 2.5, you get an approximate idea of the electrical energy that's required for cooling. Okay. I was going to show you a couple of other things, and I'll do that now. And that was that if you, before you ran the simulation, you can choose a number of outputs. Okay, so if you go to the output tab, you can then ask in the summary tables, you can make some choices. Okay, so you've got yearly reports, and you've got monthly reports. Okay, and even on the top here, you can yeah, that's okay. So let me put, so you can ask for peak space gains. You can look for, I mean, some of these are not useful at this point because we don't have chillers and boilers, towers, and so on. But see, it's reporting all those window outcomes because I had switched them on. And you can look at, you know, what is the maximum and minimum conditions on the outside and so forth. Okay, so I will turn on a couple of other things. Yeah, I think I did zone, peak, and then probably not so much that, but this one is probably a good one to have. Let's have a look. All right, so any questions on how we set up the simple air conditioning model? We'll do detailed one next seminar that we have, but that's the simple air conditioning model. For most things, I would suggest just use the package terminal heat pump, the PTHP that I showed you. That's fine. Just make sure you have ventilation turned on. Okay. Oh, and be careful. You need to ensure that your inputs are correct at every level, zone level, block level, building level. Your inputs should be correct. Otherwise, you may get some erroneous outputs. Okay, let it let it
I have
generate.
one more question, if you want to take this. Yeah.
Okay, please share some light on the radiant fraction values as part of scheduling. I'm not sure I understand this question. What radiant fraction are we speaking about? Can you put a little bit more detail in that question? I'm going to cancel that and look at the HTML file directly. Someone want to, can that person please give me some further detail? Okay. Let's see, there's one more. Okay, Amanda, I'm not seeing another, any.
Right. Yeah. So let's continue and then probably we could.
Yeah, if somebody asks that again, we can,
Yeah.
So by ticking those boxes, I have now started to get more outputs. So it asks for the peaks, space gains monthly. So it will give me that. What's the highest gain for the energy that's required? And then this is probably a useful one, the energy consumption for district heating and cooling monthly. So you can see here that it's giving me the kilowatt hours that are required for cooling. And it'll tell me what's the maximum at that point in time and when did that happen in each month. So you can see here in January, 46 kilowatt hours energy and 33 kilowatts maximum. And that happened at January 1 o'clock in the afternoon. So if you looked at, say, May seems to be the highest one. So 12,664 kilowatt hours. And you needed 58.4 kilowatts at that point for the maximum. And so on, okay? So you can see how that varies. Now, one thing I wanted to show you, which I didn't last time, was that it will give you a listing of temperatures. So this is an air temperature listing. And the next one is the radiant temperature listing. Now, I should see most of my hours, well, not most, because it's listing the whole month. It's actually listing for me all the hours when it's either conditioned and not conditioned. If I just wanted it during the conditioned hours, I could go in there and before I rerun it, I can just ask it to report only during when somebody was occupying the building. And when it does that, then that table that you saw will be only for, won't be for the whole time, but it will actually be for when there are people in the building. So let it finish the simulation. I'll pull up the results and then go from there. Okay, is there any more questions?
Yeah, we have another new question.
Okay, let me see that. If you're providing a mixed mode system, can we do the analysis on hourly basis based on the occupancy hour that in this particular hour require the system to be on, and accordingly we should calculate the energy consumption which can be compensated with help. Yes, mixed mode actually does that for you. So when you switch on mixed mode, it automatically decides when it should be in natural ventilation and when it should be in air conditioned mode. And for every hour that it's on air conditioned mode, it will calculate the energy consumption and total it up across the year. Okay, so you're exactly right. Now I don't need to load these results. Okay, so I'm going to open that HTML file one more time, and I'm going to look at those hours. Okay, yeah. So now you can see the number of hours that it's reporting is less than the number of hours in a month. So it's only when people are occupying a space. And you can see this is January to December. And you can kind of see how the temperatures are. So most of the temperatures are following, during occupied times are falling above the 21 minimum limit. And most of them are being controlled by the air conditioning system. There are some hours above, but most of them are being controlled by the air conditioning system till about 24 degrees centigrade. And that you can see very carefully, clearly as you're doing the runs. Now it seems like the hottest temperatures are in these 3 months. Okay, so March, April, May, which is what we thought it might be. And you can do things like oversize your air conditioning system slightly to capture most of those details. Here the problem is that we don't have zoning. And so it's looking at an average temperature across the whole floor plate. And it's a very hard thing for the air conditioner to do, because, you know, at any one time, some part is going to be too hot or too cold. In this case, hot. Okay. So hopefully we've covered what we need for air conditioning. Okay. Have we got any other questions? Okay. What is the strategy for designing in cold climates? Really, that is your passive solar design strategies. So you must have windows that can collect the sun in the winter. So south-facing windows that are not shaded in winter. And then depending on how cold or how warm summer is, you may need to shade the windows in summer. And when you have winter, then heat loss from the building becomes important. Okay, so heat loss from the building. I'll stop sharing my screen for a second. Where am I? Yeah, so heat loss then means your building fabric needs to be really good. Okay, so then the U value needs to improve. Needs to improve means it becomes less, so the thermal transmittance becomes less. Okay, so it's a combination from there. Now there's a couple of questions I seem to have.
Yeah, there's one question in the chat window, PC.
Yeah.
So Shalak is asking, do we get the EPI from the simulation or we have to calculate it?
Okay, so that, where's it go? In this HTML file that I was looking at, oops, sorry, wrong one. That one, where it gives you the energy performance.
Can you see your screen? In case
sorry. I always think that it's thinking like me and it doesn't. Sorry, I just opened the HTML file again, where I was showing you that energy. You can see here. So there are some source calculations, and some site calculation. So it gives you the net conditioned area of the building and total building area. So if you divide them up into zones and you say some zones are unconditioned, it'll take it off. And then you can use these numbers. Okay, so you can see this is an EPI. So energy per total building area, energy per conditioned building area. The only thing is I suggest you do a hand calculation to check, because if you put in ceilings, what's the right, attics, I guess, then the floor area of the attic also gets included sometimes. So you just do a calculation, convince yourself that this is the correct area that's down here, and then you can use these numbers. Okay. All right. So if there are no more questions about this, Amanda, how much time do we have left?
So we have 30 minutes and 15 minutes Q&A.
Q&A, okay. So let's take a 2-minute break, everybody. Maybe 5-minute break. It's 5:55 on my clock. Your clock must be 25 something.
12:25, yeah.
12:25, yeah. So 12:30, let's come back and we'll look at natural ventilation. And then we'll do natural ventilation, and I'll show you a little bit about mixed mode as well. And then we can do some QA. Okay?
All right, yeah, sure.
All right. See you in about 5 minutes, 4
Yeah.
minutes. Bye. Okay, everyone, I'm back. Hopefully everybody else is as well. I'm just quickly checking. Okay, there's no news. Okay. So this session, hi,
Mansi, just
Amanda.
let me know when you would want me to share the file that needs to
Yeah,
be
you can do
Should I
that now, actually. Yeah,
Okay.
do this now. Okay.
Sure, yeah.
So this session is really quite important. So if you're doing anything with natural ventilation, mixed mold, whatever, you really, I hope you can tell your friends as well, you should watch this session. Okay, so what we're going to do, Amanda,
PC, you're not sharing your screen.
I'm just going to, hang on a minute. I'm just opening a file. Yeah, okay, here we go. So in this session, we're going to look at how to set up DesignBuilder so your natural ventilation analysis actually is reasonable. Okay. Now, if you've attended the earlier webinars, I'm opening a model where which we had looked at previously. Here we go. Okay, so which we had looked at previously. I'm going to work from there. But Amanda is sharing a tip sheet, and you guys can download that and use it. But I'll work through that now, and then that'll allow you to set up a model that works. Okay. So to just show you, it's this same model that I had used before. There are 2 floors. This one is set in Delhi, right? So each floor is exactly the same. If I go to the first floor, there's 3 zones. Okay. Living, kitchen, bedroom, and exactly the same for the ground floor. And the only thing that I've done, which you can see if you go into the building level and have a look at it in that visualize mode, either this model view or the rendered view. Let's take the rendered view for a second. The only thing different that I've done is that on this model, I'm just going to take the roof off. We can look down. Is I have cut a hole in the slab. So you can see this, there's a ceramic tile floor, which I put on the ground floor simply so that you could make out the difference. And what that is a staircase, or at least a place where the staircase would be, and therefore the cut in the slab because of that. And the reason for doing that is, of course, if there's natural ventilation, then warm air moves up, or wind-driven air goes through the building and may move up through that staircase penetration in the slab, and we want to account for that. Okay, so that's the difference. And if I open the tip sheet that I've just shared with you, it actually tells you how to set up a building so that the natural ventilation calculations will come on correctly. Okay, so and open this up. Here we go. Right, I'm going to bring it across. So you'll have this. Amanda has shared this with you. You'll have it, but we'll just work through the steps. Okay, so I've just given you a series of things that you should do so that your natural ventilation calculations will work correctly. Okay. Now, typically when you have the default model in DesignBuilder, natural ventilation is not being calculated. It is being scheduled. Okay. But because the mathematics are quite complicated to do that. So what we're going to do.
Sorry to interrupt, but the tip sheet that you have shared looks different from the one that you're sharing on screen.
Oh,
so
okay.
Probably, yeah, I think you might have shared
What
it
is
wrong.
what is the one that I've shared? What is the title?
Yeah, so you have shared the recommended DesignBuilder modeling sequence for natural ventilation and passive solar analysis.
Ah, okay. I see. Okay. Where did I get that from? I've sent it to you, so let me pick it up from the email and
Okay.
I'll look it up right now. Okay. Sorry about that.
Or if you want, we could share it later with the students.
Yeah, no, I'm just thinking whether the one that I sent you by any chance is actually a more recent one and might be better.
Oh, okay. Okay.
So I just want to
Probably,
check that. Yeah. Because the one I have open is, I think the one that I've got is actually, yeah. Okay. Okay, I do need to share this one, which I've given you. I'll send you that. Okay.
Sure.
But let's just work through it right now. And
Okay,
then
yeah.
we can. Okay. So again, if you've been attending the previous ones, you'll know that if you want to change the options in a model, you need to go to this model options icon on the top. Okay, so I'm going to go there, and what I have done already and you will need to do is, in default mode, this natural ventilation arrow or arrowhead will be on the schedule, and you just need to push it to calculated. When you do that, it tells Energy Plus that now you must use the real calculations to work out what's happening in every zone. So it will see, is there a window from which air can come in? Is there an opening from which air can come in? What is the wind speed at that hour? Which direction is the wind coming from? And then it will work out the actual natural ventilation outcomes. Now, second thing that you must do, and you might want to do that for all your models, actually, not just natural ventilation models, is that by default, this checkbox comes switched on. Okay, it says lump similar windows on a surface. And we really don't want to do that. We want every window to be modeled correctly. Why that was done was that when computers were expensive, Energy Plus gave you an option where if you had exactly the same size of window on a wall, it would model only one window, then it would multiply by the number of windows. That's perfectly fine for energy, not fine for natural ventilation. It's also not fine for energy if you have shading on the building where only part of that wall is shaded. So really that we really shouldn't be doing this at all. Okay. So these two things you must do. Then we need a couple of other things, okay? First of all, what I've done is in the HVAC tab, to start with, I'm going to say, don't put any air conditioning, okay? So I can start like that, okay? And you just want to make sure that that has been applied everywhere, okay? So if you look at the different zones, you can see I don't have any air conditioning system, but I do want to turn on natural ventilation, okay? So you want to turn that on here, okay? And that'll allow the zones that we are looking at to have use the natural ventilation. Now, what I'm going to do is, for starting off, this green tab is only for sizing, so at this point it doesn't worry us too much. But I'm going to allow natural ventilation to happen all the time. So I made a schedule called always open. And basically I've said here that this natural ventilation is happening all the time, or it's available to happen all the time, okay? And how it will happen will depend on how you put a control strategy on it. And we'll come back to these other ones later on. And you can see here, this is the mixed mode button. So once you know that your natural ventilation is working correctly, you can switch on mixed mode, and then it will allow an air conditioning system and natural ventilation to happen. And when we switch on mixed mode, we will actually add an air conditioning system on the tab as well. So right now, no mixed mode, no air conditioning system, only natural ventilation. The other thing you might want to look at, and all of these are in that in the tip sheet that I've shared with you. I'm just going through them step 1, 2, 3, 4, 5, 6, 7, right? So don't worry, you'll get them all. The other thing you might want to do is on the construction tab, once you switch on natural ventilation, it will actually ask you how good or how bad is your construction? How tight is your construction? Is there a lot of air leakage? Okay. Now in India, I would say either do very poor or poor. We really don't look at the infiltration, or air leakage is not a really big thing that we look at in India. Unless you do something particularly for controlling that, don't take it above poor. Okay, so that one is done. Then the last thing, well, one of the last things really, is if you go to the openings tab, what you'll find is that once you switch on that natural ventilation calculations, you will get an additional item here under Windows, okay? And that additional item is called operation. And so what it asks you is that, how do you control the opening and closing of windows? And there are some options here. One is that when it's occupied, open the windows. The other is you put a special schedule. So what I've done is that I've used this always open. So initially I'm just going to do a run where the windows are open all the time, okay? And you can then control how much of the window is open. Is it 5%? Is it 10%? Is it 50%? Half of the window? You can never get 100%. Okay, so 85%. If you got windows that open fully, from the frame about 85, 90% you may get. 100% you don't. Okay. So here I've said 50% of the window opens. And this left and right just allows you to specify whether, you can either do top or bottom or left or right. So you can pick anything. In many European countries, not in India, you will have windows that only open from the bottom. You have a little winding thing that opens the window just a little bit. They don't open windows like we open in India. Okay, I'm going to leave it as left because typically in India we have shutters which open out, so we can open a fair bit of the window. I'm going to allow 50% of the window to be open. Okay. The discharge coefficient, if you don't know any better, that's fine. Okay, so I'll leave it there for now. Okay, so what have I done? I've told Energy Plus, switch on the natural ventilation calculations. I've said in the window schedule, I want it to be always open. Okay, so now what I'm going to do is I'm going to run that building. And it's in Delhi. So I want to I want to test something. I don't want the whole year and then try to figure out what's going on. So I'm going to do only 1 month. And I've decided I'm going to do March. And the reason I'm going to do March is it's a swing month. It's what we call an in-between month. It's not really that hot. It's not that cold. It's, if natural ventilation was possible, then March is a good month to try and test what's going on. Okay. So the other thing, I'm not sure I've put it there. I better add it on if I haven't done it before, is you need to store this surface output. Okay, temperature distribution, surface output. This is important. Okay. And if you want any of the adaptive comfort standards, you can turn that on as well. But initially, maybe just that. And I've said, okay, tell me all times, what is the temperature, what's the environmental conditions. Okay. So if I now run this, and this time I'm going to allow DesignBuilder to load all those files back into the interface. There's a reason for that. Okay. So it will run the 1 month simulation. It will load those results back, and then we'll start to look at some of those numbers. In the meanwhile, I think there's a lot of interest that you guys have got on mixed mode and natural ventilation. I just ask you to be careful because there are, when you're doing the calculations, it's quite complicated, although everybody wants to do that. And if you don't have the appropriate values set, then your results won't be very useful. Okay, we're almost there. It's only a month run, so should be good. And first, I want to show you what we can see in the DesignBuilder interface. Then I'll take you to the HTML file and the hourly file. Okay. So now, some things to look at which are quite useful is that we only have electricity for equipment and lighting. We have nothing for air conditioning because we didn't specify any air conditioning. Okay. The other thing that we can see here is that during the high points, during the high temperatures, and we can look at first room living area, so the top floor living area, you can see that at the peak of the day, the annual air, the room air temperature and the outside temperature are quite close. Okay, so the room is kind of following the outside temperature, right? If you see this week here, you can see that every day is slightly warmer. So these 4 or 5 days, the outside temperature is getting warmer up till that point, and then drops off and then starts up again. But anyway, so you can see here that at some point, the outside temperature starts to fall, but your air temperature and your radiant temperature continue to be above the air temperature and reduce slowly. Now, when you have this kind of effect, you know your natural ventilation system is working, okay? If you see some very big differences between the air temperature and your room temperatures, then you know something is wrong. Some setting might be wrong. And here what you can see is that there's natural ventilations happening at different points in the day. You look at no 2 days are exactly the same, and that depends on the wind. So if there's wind and it's in the right direction, ventilation is going to happen. And also if you look at these numbers, you can see these numbers are very much different from when the air conditioning happens. When you're doing air conditioning, you might be lucky to get 2 or 3 air changes per hour. You can see here that you're almost getting 100 air changes per hour. So there's a lot of wind suddenly at the right direction for a short amount of time. You get a huge amount of airflow. Typically, it might be much less, but you're getting these bursts of big ventilation happening through the building. Now, if you set it up correctly and you asked it for all the surface outputs, then you can visualize what it's doing. Okay, so that's the reason for looking at the DesignBuilder interface. You can see where the wind is going through. This is not CFD, by the way. The picture that Mansi showed us, that was CFD. CFD was a bit like this. Okay, so in a cross section of a building or on the plan of a building, it actually gives you some idea of where the flow vectors are. Now that's for one specific hour. CFD you generally do for one specific hour. Okay, this is much more about what's happening on average every hour, and you can keep changing the hours. So 6 p.m., 7 p.m., and you can see that it changes all the time. 8 p.m. It's at every hour, okay? And because the wind direction and speed are changing, then the impact it's happening on this building is different. Okay, so this is a very windy hour, and the wind just happens to be right at the correct direction. The wind direction is pushing air through there, and you can see a lot of the wind is coming up from the bottom to the top floor through that staircase hole that we cut. And it's actually telling us, so if you went to first floor, then you can work out how much air is actually going out and coming in during that hour. So you can spin the model around and you know how it's working. Okay, and you can do that literally everywhere. So you can go to a room, or you can go to a whole building, and you can figure out what's going on. And that black arrow, which is really quite big, means there's a lot of airflow coming from the bottom floor to the top floor. Okay, so that black arrow on the inside is the transfer of air between the two floors. Okay, now is this, what kind of effect is going on? Okay, and you can look at that in a little bit more detail. So if I go back to still in the DesignBuilder interface and I look at just a wall, so if I look at the north facing wall and I look at one of the windows, it will actually tell me, you know, the blue is airflow in and the red is airflow out. He hasn't really written the legend very well, but it tells you that, you know, in the earlier part of the day, most of the air is coming in, then there seems to be some sort of a wind shift, and then it reverses. Okay, so this is from that window, and because we checked the report subsurface values, it will show you that. Just remember, when you switch on surface and subsurface data, it creates a really massive file, and to load it up takes a lot of time. So I seriously recommend to you that use it for testing your design at certain points. You do a week, 2 weeks. That's sufficient for what you need to know, and the model will load earlier. Okay, there's some things here, you know, it's telling you what's the inside surface temperature of the glass and the outside surface temperature of the glass compared to the outside temperature, right? So some of those things are useful to see. But what I wanted to also show you was that if I picked up the Energy Plus results, direct raw results, then Energy Plus will load both the HTML file and the hourly reports. Okay, so you can see the site energy dropped a huge amount because there's no air conditioning, heating, or cooling. You have absolutely no heating or cooling numbers in this district cooling, district heating table. You still have lighting and equipment in the electricity column. Okay, if I go to hourly, then all of a sudden you see there's a lot more stuff being reported. This is actually the what we call the airflow network, and it will actually tell you if there is air movement between one side of an element, windows, doors, walls, ceilings, whatever. It will actually show you the airflow going from one side to another. Now, that's quite difficult to kind of look at, right? If you know exactly which one you want to look at, you can. And the way to kind of think about which one it is if you want to know what this window is, you can go to the Edit tab, and under this miscellaneous, it will tell you what's the name of this window. Okay, so first floor living area, wall 3, window 3. Okay, so you can pick it up. So if you look at this, you can actually find out which one it is. So you can see here, there's a wall 3, but this is 003. We want 300 windows. So, and you can search by area. So it makes it a little bit easier to do that. But again, you really don't need this unless you are specifically looking for something. Okay, you're better off looking at things like temperatures because they give you the outcome of what you're doing. So if I look at some temperatures, let's have a look. Report type, zone, air temperature. Here we go. So I'm going to do two things. One, I'm going to plot the air temperatures, one for the ground floor, the living room, and then the air temperatures again, but for the first floor living room. Now, before I plot it, anyone want to have a guess? Is there any difference between these? Will there be a difference between the ground floor and the first floor temperature? And why would there be a difference if there was one? Somebody want to put something on the chat? QA? Why would that be there? And should there be a difference? Okay, somebody says yes, there'll be a difference. Why will that difference be there? Anyone else want to have a guess? All right, let me plot it for you, and then you can tell me why there's the difference. So I'm going to pick this 4 days where the temperature keeps on increasing. And what I might do is, just to make it interesting, we'll plot the outside temperature.
You can
So
see
now
some responses in the Q&A window. Yeah.
Okay, let me have a look. I was looking at the chat window. Somebody did say, okay, there'll be a difference because of height difference, because warm air rises, difference due to higher solar radiation. And there was one in the QA where there was one more in the chat, I think. Hang on.
Yes, one in the
somebody
chat,
said ground floor will be cooler as compared to first floor. That answer is spot on. Okay. So why is that? Why will the ground floor be cooler as compared to the first floor? You have experience. If you're living in 2-floor houses, you know that. Why is that so? So you can see here the red line is the first floor and the blue line is the ground floor. Okay. And the green line is the outdoor temperature. And as you can see, as the outside temperature gets hotter, the temperature difference is even bigger. And the red line, which is the first floor, is warmer than the ground floor. Yeah. That's because the first floor is actually shading the ground floor. So all the solar radiation that's hitting the roof on the first floor doesn't come into the ground floor. Okay. And here's a classic example of what they teach you in passive solar design, that if you do shading, number one, you reduce the peak. So you can see the blue line, which is the ground floor living, being shaded by the first floor living room. The peak is lower than the ambient outside temperature, and the peak is shifted. Okay, so if you look at the old Koenigsberger textbook, it says decrement and delay, and you can see that exactly happening here. Okay, so the peak of the outside air temperature, 30 degrees, happens at 3 o'clock, but the peak inside on the ground floor is at 5 o'clock. 2 hours afterwards, it's much less. Yeah, it's down here is 29 degrees. This is 30 degrees, 1 degree difference. But on the top floor, it's even hotter than the outside. Okay. They're all 1 to 2 degrees, but they are significant. Okay. Now, what I might do is, this is the air temperature. So just for the first floor, so that we don't confuse ourselves, I'll plot this is the air temperature. In fact, I might change the colors. So let me plot the first floor air temperature, and then I'm going to plot the first floor radiant temperature. Okay, so now you can see what's really happening. This is the red line, the radiant temperature is what you feel. Okay, so while the air temperature looks okay, not too bad, but because of the radiant temperature, you're feeling much hotter than what the air temperature is. Okay, so you can test that using the natural ventilation thing. And what we've done is we've left the windows kind of open the whole time, 50%. Now, one of the reasons the temperature is not coming down a lot is because I've actually changed the ground temperatures. Now, I haven't shown you that. Let me show you that now. And the reason I've done that is when you're doing calculations for natural ventilation, when your building is sitting on the ground temperature becomes very important. Okay. Why? Because the ground acts like a sink or a source of heat. Okay. So if I'm at that level, and again, if you're doing smaller buildings of any sort, you must pay attention to for any building, I would say, you must pay attention to the ground temperatures. So this ground modeling, okay? So what I've done is I have changed these monthly temperatures. Now the way I've changed it is not the best way, but I did it because I was in a hurry and I wanted to show it to you. Okay, you will have to do some research on what you want to use. Now there is a model that Energy Plus has incorporated called Kiva, and Kiva Basic actually does provide the best outcomes, but it's still not there yet. So you might have to do standard and do a little bit of a change. What I did, okay, because I thought I should do something, otherwise the differences are too big, is I looked at the weather file. So I went to the Energy Plus weather data folder, and I looked at for Delhi, and you'll find them here, India, Delhi, New Delhi, ISHRI, and then this statistics file, which I opened using a text editor, has got a lot of statistics on the weather file that you're using, right? If I go right down to the bottom, somewhere near you'll find these values, monthly calculated undisturbed temperatures. Okay. Now, typically, it will actually tell you that these ground temperatures must not be used in the ground temperature object. Okay. You can use the temperatures for 0.5 from ground temperature surface, and you can use the 4 meter for ground temperature deep. Okay. Now I was in a rush and I didn't do it correctly, so I just put in the 4 meter one everywhere, which is not the right thing to do. What you should do is for the deep, use the 4 meter values. For the shallow, use the 0.5 meter values, and possibly use the 2 meter values there. That'll give you a reasonably better outcome than what I'm showing you right now. Okay. Why is that important? Because if you're in a cold location, particularly, or cooler location like Delhi can get pretty cold in winters, then the cooling demand will be suppressed and the heating demand will not show correctly if you don't have the right ground temperatures. The reason this is a very difficult topic, and you'll see lots of research papers on it, is because The ground temperatures move very slowly. Across a month, it might move by about half a degree. Okay. Once you're below the ground, it's very stable. Okay. But because you put a building on top of this, it changes the ground temperature. Again, it changes it, but it doesn't move a lot, right? What we are doing in simulation is we're doing a calculation every hour. But the ground temperature is a much slower process. You need a different calculation algorithm for it. And a couple of people have built algorithms for it. Okay, there are 2 or 3 ways of doing it. In Energy Plus, you should read what are the different options for doing ground modeling calculations and pick either standard or pick ground domain. These 2 we know work. Okay. Kiva has still got some bugs in it, and they're still working on that. So use either the standard one or the ground domain, but please read the documentation to decide which one is better for you to use. Okay. Anyway, too much time spent on ground. Let's go back here. So you can see what's going on here, right? Now, by doing your changes, you can improve the building fabric, okay, so that when you start to look at the hourly temperature, sorry, don't need to be there. If you look at the hourly temperature distributions, you can improve them to be not too hot and not too cold. Okay. Once you've done the passive one correctly, then you can switch on the air conditioning and the mixed mode to see what is the energy that you might need to compensate for those hours where you have not been able to correctly account for it. Okay, so where do you see those temperature distributions? Well, right here, you can see it has, because I've asked it to plot the temperatures, and I've used the schedule called on, so it's reporting 24/7. You can see what's going on here. So you can look at that case, the living temperatures. And I've only done March, so only the line of March has been filled in. And it's giving me, there are 18.5 hours between 19 degrees centigrade and 20 degrees centigrade in March, and so on. Okay, so there are no hours that are higher than 32 degrees in March. That's why I said that if there's any month when natural ventilation can best be utilized, it's probably March or September or October or something like that. Otherwise, you really can't open your windows. Now, how do you adjust? How do you control your windows? Well, you've seen that. If you go, and you can do this for each individual zone or each individual window or the whole building, you can go to the openings tab and you can set your own schedule. Okay, so how you can control the windows, right? Now, there are other control strategies that you can look at. If you look up the help file, sorry, where's the help file? If you look up the help file and you search for natural ventilation, so support, yeah. If you look for natural ventilation, there's a whole series of things available on how you can do natural ventilation. So you must read it to make sure that you are doing it correctly. Okay. And one way of testing it is what I showed you. If you leave the windows open 24/7 and you leave, say, 100% of the windows open or 50% of the windows open, then the internal temperatures should follow the external temperatures. And what you can do is you can test it by, say, close the windows during a certain time. At that point in time, because you close the windows, the temperature, something should change in the air temperatures. Then you know your strategy is working correctly. So here it tells you calculated natural ventilation options. Okay. So, and please do read some of these things. Don't just blindly go and do things, because then your outcomes won't be very reliable. You do want to be able to do a proper job when you're doing that. So you can see here, okay, types of options that are available, controls that are available. How can you tell when windows should be opened or closed? Either you do a simple schedule like I did, or you can actually say things like, okay, when the temperature difference between the outside and the inside is so many degrees, open the window, and how much you want the window to be open. So there's a lot of options available, very powerful options available, but you must really read them before you put them in, because you can't just click a few buttons and go, yeah, I'll do this, because that is not going to give you a useful outcome. Okay, so have a look at this. Anyway, just go to the help file and look for calculated natural ventilation data. You can see what all is available. So control choices are no ventilation, temperature, enthalpy, by schedule, by some of the ASHRAE 55 adaptive temperature model or the CEN adaptive temperature models. These are for all your external windows and then even for some internal windows. And then here you can actually say that you can open the window based on the temperature difference between outside and inside. If there's a very big temperature difference between outside and inside, you don't want to open the window fully, because then the person sitting inside will suddenly feel really cold. So it will allow you to open the window just a little bit when the temperature differential is very large, and then open the window more when the temperature differential is less. Okay, all of that's available. You just need to read through and decide how you want to do the control strategy. Okay, now once you know that that is working well, then what you can do is you can go to the HVAC tab. You can switch on air conditioning. And again, I would say do something as simple as PTHP, package terminal heat pump, switch on mechanical ventilation, put a correct set of schedules. Okay, be very careful that you don't make mistakes on the schedules. And once you put the correct schedules, you can switch on natural ventilation and you can switch on mixed mode, and then it will take the thermostat range and try to keep the building in that range. You can make the range a little wider. I would suggest 18 to 26 or 27 or something like that. So during that time, the natural ventilation will work. And then outside of those times, the air conditioning system will come, the ideal air conditioning system will come on and do those, do the heating and cooling for you as you need it. Okay, I think that's probably as much as we can cover today.
And yeah, we have one question on the
Sure.
Q&A window, and one is a comment. So let's take up the question.
Yeah.
Once we calculate the hours, the first one, which is once we calculate the hours required for mixed mode, then we should incorporate that for simulation. It's more like a comment, but
yeah, no, it is a kind of question. So the answer to that is that once you do this correctly, you don't need to calculate the hours when you need mixed mode. The simulation will do that for you. Okay, because the whole idea of a mixed mode, and I think there is actually a description in the help file for the kind of mixed mode that DesignBuilder uses. It's something called a changeover mixed mode. Let me see here. Yeah. So there's a definition here for what mixed mode is. Okay. And there are some 2 or 3 kinds of mixed mode buildings. And DesignBuilder can model all of those 3. Okay. The one that we most usually do is what we call a changeover mixed mode. So what happens is that when the conditions are right, then the building opens up, literally. The air conditioning system switches off, and natural ventilation does what it can to keep the temperatures in the range that you've defined as comfortable on your thermostat setting. When it feels that the temperatures on the inside are actually getting either too hot or too cold, typically too hot in India, I would say, then it says, okay, now with natural ventilation, I can't maintain temperatures. So I'm going to close the building and I'm going to switch on the air conditioner. That's this changeover mode. Okay, so it's looking at the outside, it's looking at the inside, and it's making some decisions based on how you define the control strategy. That control strategy setting up is very critical for you to get some realistic results. That's why I'm saying first do just an air conditioning run, then do just a natural ventilation run. Then when you know both of those are working, switch on mixed mode and then do adjust the control parameters and then see what you get. And in some ways, I would say pick even a week when you know mixed mode will work and do your diagnostics on that week, because then you can see very quickly the simulation runs are fast. You don't have a lot of data, so you can graph it all and look at it very carefully. When it's working well, then you can turn off all the surface variables, because otherwise you'll get this huge file, and then you can run it for the year. Okay, so there's a bit of effort when you start to do mixed mode, and really when you do mixed mode so that the results are representative. There's a lot of simulations which put out real garbage. Okay, you don't want to do that. You want to be sure and confident that when you do a simulation in mixed mode, it is actually working correctly. And that is hard. It's not easy to do that. It's not easy because the mathematics becomes really complicated. You have, when you're doing air conditioning, it's simple. You know how much air is coming in. There's a fan. The fan brings the air in. You can calculate that. When you do mixed mode, you suddenly have to do heat transfer calculations and you have to do mass transfer calculations, because the airflow brings mass and the mass brings humidity and heat. And its control strategies dependent on 2 or 3 things happening together. So it's complicated. I mean, in real life, it's easy. You feel hot, you open the window. If it's cooler outside, it works. But mathematics is a different thing. Okay. All right. Sorry, Amanda. Anyone else?
So PC, yeah, so that was the last question, and I think most of the questions we have taken up in between the sessions. So yeah, so that was the last question. So we could end the session unless you want to add some last note or comment or anything to the students.
Yeah, I think it's pretty good. I think there's only 32 students who probably joined. So that's interesting in itself.
There were more who joined, but yeah.
Hopefully they'll because I feel this is a very important session that they should go back and review, and maybe applicable to many of the projects that the teams are doing. So it'll be great to see how they can use this part of the simulation correctly. I think this year they'll be looking very carefully. The judges will be looking very carefully at your outputs and seeing whether they make sense or not.
Yeah. All right. So thank you so much. Thank you, PC. And thank you so much, everyone, for joining us today. In the next webinar session, we will talk more about various kind of how to model various kind of systems and more detailed HVAC systems. And yeah, we will see you next on the next technical webinar, which is the 6th technical webinar on designing right size HVAC with load calculations.
So we'll do two things. We'll look at how do you set up the model so that you can actually work out correctly the size of the air conditioning system you needed. And we'll quickly look at two detailed air conditioning systems. We'll look at one, a VRF system, because there's a lot of interest in VRF. And we'll look at one big chilled water system with chillers and boilers and fans and all that. And that will hopefully cover pretty much the lot of what we're going to do with DesignBuilder. So yeah, come prepared, hopefully.
Yeah. All right. Yeah. Thank you. Thank you, PC.
Thanks
Yeah.
then.
Bye, everyone.
Bye, everyone.